they've done this. If we look at memory locations beginning at 0 down there, and we go up to 00FF, that's 255 locations, well, 256. These are reserved basically what we would call trap vectors or interrupt service routine vectors. It's kind of interesting where the term vector comes from, because on this system, all you have, and we can take the trap 25, which is a halt. What that really does, it's almost a subroutine call. It differs a little bit. It's kind of an indirect subroutine call, I guess. It doesn't transfer. See, if you had a JSR up here, a jump subroutine instruction, with an address like that, it would go to this address and begin executing. That's not what happens here. What you have is that location down in here someplace is 0025. What that thing actually holds is an address that gets us up into here someplace. Let's see, in the book they give us the actual address of what that holds.
At page 221.
Yeah, that's about right. I'm on 222, so. Yeah, FD70. There's really no need to remember something like that, just to remember how this thing actually operates. So what this thing holds is something that points to something else, okay? Well, that's what vectors do, they point. One of the reasons why the thing is called a vector. Another one is that on a lot of more complex machines that will actually contain two words down here, one of them being the program counter where the service routine begins, and another one changes. Remember I gave you this term of a process status word, which defines a number of things about what's happening to the process that's currently being run. One of them is the priority. And as you go to execute, let's say, an I/O routine up here, that should be at a higher priority than ordinary computation things, because they don't work well if they get interrupted. Think about two different people. We can think in those terms. It could just be two different processes that both want to print something out to the terminal. And they call it at the same time, but they keep getting interrupted by the other one. And so you get a character from one and a character from the other, and then one from the first one, and everything gets mixed together. You can't have that. So you have things set up so that the I/O routines run at a higher priority, so that once they get started, they can't be interrupted. Okay, so those vectors consist of two components, just like a vector in the XY plane has two components. One in the vertical direction and one in the horizontal direction if you wish, but these are a little bit different. So that's where the term vector comes from. On this system, all they have is just a single word. And so when you execute this trap, it goes to whatever location you specify out here, fetches the contents of that location, puts that in the program counter. Okay, so here's the sequence of events that actually happens when you execute this thing. It gets just a little bit complicated. You go to memory 0025, load the contents to the memory data register. Remember, that's the interface between the processor and the memory. You've got an address register and a data register. Actually, what you do here is you put this thing, put that gets put in the memory address register. Then you move the contents of the program counter to register 7. Then you move the memory data register to the program counter. Now, for a halt routine, this isn't significant. But if we look at a different one, 21, for example, 21 is the in routine. No, 21 is out. If we say, in the course of our program here, someplace we have out, we'll talk about what this routine actually does here in just a minute. That's equivalent to trap x21. But then you're going to have more in your program. That's not true of the halt. So this thing functions just like a subroutine, a subprogram. It's very much a JSR, except that you don't go to, it doesn't put this 21 in the program counter. It fetches a thing out of memory, holds on to it for a minute, saves that program counter, and then copies that value that's out there. Out is in a different place. It's 0430. Here's where the out routine is. And so 21, 0021 down here below it actually points into this location. Now out, halt, it's just going to shut things down. And so it doesn't return. But out will end with a return, RET. The service routines end with a RET, except halt. And what does this do? Well, all it does is to copy register 7 into the program counter, so that it gets back right where it left off. As it's executing this, the program counter contains the address of the next instruction. Well, you save that. You go down here and execute all this stuff in the service routine, whatever's in there. And then when you execute this thing, it copies that saved value back into the program counter. And so the next instruction to be executed is right here. See, we think in terms of the execution of that thing always just proceeding from one instruction to the next. No, it goes from one instruction to whatever is in the program counter, or to whatever is contained in the memory location whose address is in the program counter. That program counter is always pointing to the next thing to be done. And so when you change that, that's the thing that interrupts the flow of control through the machine. Okay, so the basic layout of this whole system, you've got some stuff down here at the low end of memory that's saved for operating system routines. You got some stuff at the high end as well. And so this stuff in between is basically the user area. Now that's why, for example, when you write your routine, your function, your programs, and you say origin with some semi-arbitrary value, it puts you in here somewhere. You can't start down here at 0 because that'll mess up all of these things. You can't be too high up because it'll mess up these. But within a range here, you can play with it a little bit and use it however you need to. Okay, that's the basic layout, and it's a fairly typical layout for a lot of systems. Not so much the Intel system, however. It is significantly more complex than that, the way it works. Divides things up in a very interesting way. Anyway, that's how the trap routines work. Let's see. We want to talk a little bit about in and out as a way of handling things. There we go. Trap routine for halt. They actually defined in and out there in that chapter, but I guess they don't. In and out do not function like CN and Cout in C++. Not at all. Let's see, since we've got out here, we'll do that. Basically, what this thing does is it prints the ASCII character in register 0, that's 0 to 7, to the display. So what does it do for you? Well, frankly, not a great deal. You don't have to write in the wait loops to wait for the display to be free and work with it. But you cannot just take a memory location and say out on that thing and have it do the conversions and print the thing out. It prints a single ASCII character. Okay, so if we write our semi-traditional first program, print hello world, we might do this kind of thing here. Put a label of some kind on it, doesn't matter, whatever kind of a label you want. We can do the following. We'll say register 1, label 2. Then let's see, I will load register 0. Relative addressing relative to register 1. In other words, what I'm going to do is fetch in the first character in this string, namely this uppercase H, into register 0. Now, right at this point, I'm going to check for this 0 word at the end of the string. Once I load that 0 word, I'm going to jump out. Otherwise, I'm just going to print the character that I just loaded into register 0. And I'll put label 1 up here on this instruction. Oh, no, let's see, I got one other task to do before I do that. I've got to increment my pointer register that's telling me what I'm going to actually be looking at. And then I'll do my unconditional branch to label 1. Okay, if you look at how that thing gets set up, I don't have a starting address on it. For the sake of discussion, we'll write a starting address of 0. Load effective address, label 2. And so then 1 is the load relative, 2 out. 4 is the add branch. 6 is the halt. And so now 7, 8, 9, 10, 12, well, see, these are all done in ASCII, so I better do it there in hex. As we go through this thing, this is what we're actually going to find in those locations. 7, I set this up so I've got an uppercase H, which is a hex 4-8. And I've got a lowercase e, 0.065. This is an H, this is an E. L is 6C, 6C, L, L. I've got a space, which is a 2-0. The uppercase W is a 5-7. 6F is an O. 7-2 R 0-0-1-0 is an L, which is a 6C. 1-1 lowercase d is a 6-4. And then because of this thing, we have down here, and this is what I'm really after, is that byte of all zeros. If you look at the ASCII table, that's specified this way. It's the so-called null character. There's nothing there. Okay, so the way this thing actually operates then, if we trace through and execute it, you see the following. First of all, we load the address of label 2, which is at the beginning of this string. So it's the 7. That's what gets actually loaded into there. Then the load relative uses that as an address, so it fetches in this 4-8. It's not 0, so it doesn't branch. It does the out. So on the display we get an H. We add 1 to this register, so we get an 8. We do an unconditional branch back to here. Now when I load, I'm not referencing 7, I'm referencing 8. So I come down to here and I load a 0, 0, 6, 5. Not 0, so I print it and I get the E. So on. Okay? We just worked through the thing. The real benefit of the out or the track 21 is that you don't have to code and worry about the wait loop waiting to get the display free to accept the next character. But if you want something printed out, you have to generate the ASCII character string for whatever that is that you want to have printed out. You still have to do that. But the out takes care of the wait loop and the things involved with that.
That's the opcode is OUT, that's all you have to put there to do that.
Yeah, that's the instruction.
That's
just
instruction,
out.
just out.
Mm-hmm.
Okay.
Or you can use trap X21.
Okay.
They're synonymous. Now, in works in just the opposite direction. It will bring in a single character, well, okay, this is the description of it as it's put in here. We'll print a prompt on the screen and read a single character. Again, it's not a character string. If you want a 4-digit integer, it's not going to handle that all at once. Print a prompt and read a single character from the keyboard. The character is echoed onto the console monitor, and its ASCII code is put into register 0. Now, let's see. In fact, I think they actually give relatively little discussion of in and out. All the discussion on the trap routines relates mostly to halt. And then we go on to well, they don't go into any length about that, give you any kind of demonstrations with it, so. The basic idea is that it allows you to enter one character at a time.
That one.
So you can experiment with that a little bit and see what's going to happen with it. Now, I'm to get you started on another assignment here, so.
And this is due a week from today.